Hi everyone, I am Harsh Katekwar. I am currently a graduate student at Indian Institute of Technology, Mandi, and this is the pre-recording presentation of for International Cognitive Conference on Cognitive Modeling 2022. The title for today's talk is Understanding Adversarial Decisions for Different Probing Action Cost in a Deception Game via Cognitive Modeling. Cyber attacks are the intentional attempts by the adversary, and it has been exponentially increasing in the recent past. In the 2020, there was a major cyber attacks on the infrastructure of Twitter and Marriott, and these cyber attacks and the lack of security solution has uplifted the research community to develop some solution that can help in combating these cyber attacks. Though there exists some solution, but however they could not provide effective solution in the real time. So deception is the act of making someone believe in the false information, and it may help in providing real-time solution against the cyber attacks. So as we know, with the help of deception, human decisions are likely to be influenced by various factors such as complexity of cyber attacks, network topology, network size, probing action cost, and various others. Deception in cybersecurity has been studied with the help of simulation games, and recently deception has been implemented with the help of honeypots in the real world. And this technique has proven to be very efficient in combating against the cyber attacks. So honeypots are nothing but the fake system that act like the real ones, and it has been used to divert the attention of the attacker from the target. So in this experiment, we used a simulation tool called DG with, that help in understanding the adversary's decision in the various situations. So DG is a sequential single player game between adversary and the network, and which is denoted using the following notation, where n denotes the number of web servers, k denotes the number of honeypots, and gamma denotes the number of probes after which the adversary makes his final decision to attack the network. So here is the demo of deception DG211, and in our deception game we had two conditions, no deception and the deception condition. So in the no deception condition, the adversary on probing a particular web server receives the correct information about it. Like here, the adversary probes the web server 1. He gets the response as the real web server, and in the real situation, the web server happens to be the real web server. So on receiving this information, the adversary is likely to attack the same web server. However, in the deception condition, uh, in the same scenario, where in the DG211, the adversary on probing the same web server 1 receives the information as honeypot. This change in information might influence the adversary's decision, and it may lead to attacking of web server 2, which happens to be honeypot in the real world. So, to investigate the effect of different probing action costs in the adversarial decisions, we had three conditions: no cost probe, constant cost probe, and the increasing cost probe. So, based upon the instance-based learning theory, which is a cognitive theory, the human decisions are likely to be affected, and they are likely to be and they are most likely to maximize their positive outcomes and minimize their negative ones. So in the cost associated condition, that is constant cost and the increasing cost probe, the adversary when the adversary chooses for the honeypot web servers, the adversary is likely to experience negative outcomes, which overall lowers the blended value of probing or attacking honeypot web servers. However, for the no-cost condition, probing or attacking the network may not cause the adversary to experience negative outcomes. Thus, we expect that regular probe action are likely to be influenced by different cost conditions. Furthermore, the attack phase followed the probe phase, so also the cost was associated for with the probing. Not so we do not expect any difference in the proportion of attack decisions during the for different cost conditions. So we our experiment had three condition, three between in subject condition, no cost probe, constant cost probe, and the increasing cost probe. In the no cost probe, there wasn't any cost associated for probing or for probing honeypot web server, and in the constant cost probe, the cost remained same across all the same over the trials for the honeypot web server, and for the increasing cost probe, the cost for probing honeypot web server increased over time. So we had six dependent variables, three for the probe action and three for the attack action. And for the experiment, we recruited 120 human participants from the Amazon Mechanical Turk for the study, and we divided 40 in each condition. So this is the interface for the DG42X, where we had four web servers, and two of them were out of these four, two of them happens to be honeypot, and the remaining two were the web servers. So that was the participant will given with some information as well regarding the game, and the adversary had the option to choose probe of one of these, means they can probe any number of times, and they also had the option to not probe and directly proceed to an attack stage. So on probing a particular web server one, probing a particular web server, the adversary received the response as the response from the server, and based upon the response from the server, he after probing certain amount of times, he moves to the attack stage, and in the attack stage he had the option to attack one of these web servers, and he also had the option to not probe or not attack the network and directly proceed to feedback stage, where he gets to know about the response for his probe and attack actions. Instance-based learning theory is a dynamic decision-making theory for the complex situation, and it has been implemented in the area of cybersecurity by the various researchers. So an instance in the ideal model comprises of situation, decision, and the outcome. Situation basically refers to the current state in the network, decision denoting the decision made by the hacker, and the outcome is the reward associated for the decision made in the situation. So in the IBL model, the instances accumulate over time and are retrieved from the memory and blended based upon their activation values. So activation is the strength of the instance, indicating its importance at the current context. And the blending is the accumulation of multiple instances in the memory based on their activation to make the decision. So IBL model makes use of this following equation for calculating the activation of an instance, which is nothing but the strength of the instance, and the probability of retrieval is the probability of recalling the instances from the memory based upon their activation strength, and the blending value is the weighted sum of probability of retrieval and the outcome associated to it. So the IBL model instance in the IBL model comprised of three triplets: adversaries, decisions, feedback, and the outcome. And we had feed some pre-populated instances to the model: web server 1, regular, and the 70, basically denoting that the web server 1 happens to be the regular, and it has been awarded positive, and for the honeypot the adversary would be awarded negative, and if you do not take any action, then he would be just awarded with the plus 10. So I will show you the working of the IBIL model. So here on in the trial happens to be the trial 1, which happens to be a deception trial, and in the web server 1, and web server 1 in this particular example is a real web server. So the in the probe phase, the adversary on probing web server 1 receives the incorrect response as honeypot, and the outcome associated to it is -70, and the timestamp is nothing but the trial 1. So once after the probe phase, the adversary proceeds to the attack stage, and in the attack stage, let's suppose he attacks the same web server 1. So on attacking the web server 1, he receives the response as the regular, as in the attack stage he gets to know the correct response, hence he gets the outcome associated for the probe and the attack added in the +70, and also the timestamp also gets updated in the trial. So we had built two models, IBL model, two IBL models. One is the calibrated one, and the other is the ACTA model. So for our IBL model, we had two parameters, D and sigma, and D denoting the decay and the sigma denoting the noise. So in the IBL calibrated version had the we calibrated the value of D and sigma, and in the ACTA IBL Actor version, we had used the default values of D and sigma. So for evaluating the performance of the model, we use the performance metric as mean square deviation, that is average mean square difference between human and the model actions. And we tried to minimize the MSD using the optimization algorithm called genetic algorithm, and uh, we kept the mutation as at 0.01 and 0.80 as crossover rate. These are the model parameters for both the IBL versions, and we found that the IBL calibrated version had relatively lower MSD compared to that of IBL Actar version for all the three conditions. And in addition, we also found that the memory decay and cognitive noise value for for all the three conditions, and for the no cost condition, the memory decay value happened to be quite high, and the cognitive noise value was quite high for the increasing cost and the constant cost condition. Furthermore, the utility value for the regular web server and the no action was quite high in the no cost condition compared to that of cost associated condition. These are the result for the increasing cost condition, and here the x-axis denotes the blocks of trial, and basically in our game we had 29 trials, so we divided the 29 trials into 5 blocks each, and so block 1 to block 5 have 5 trials, and block 6 having the 4 trials, whereas the y-axis denotes the proportion of attack and not attack decision in the increasing cost condition. So the darker line shows the attack decision, and dark color basically denotes the attack decision for human actor model and the calibrated model, and whereas the not attack with the light color lines denoting the decision for the not attack decision across human actor model and the calibrated model. Likewise, these are the result for constant cost condition, and here the x-axis denoting the blocks of trial and the y-axis denoting the proportions, and same for the no cost condition as well. These are the results, and the experimental part showed that the different probing action cost did not influence the adversarial decision during the attack stage. And it also revealed that there was a constant pattern of regular probe decision in the cost associated condition across the rounds. So the result from the cognitive model showed that IBM calibrated version had performed better compared to that of IBM vector version. And in addition, it also revealed that in the no cost condition, we had the higher memory decay value compared to that of cost associated condition. Furthermore, the one possible reason for this could be that as in the no cost condition, the adversaries do not experience any negative experience, which makes them reliant on the game's feedback, and as a result the memory decay value for the no cost condition becomes much higher compared to that of cost associated condition. Also, the Also, the pre-populated utility value for the regular web server action and the no action was higher for the no cost was higher for no cost condition compared to that of cost associated condition. And in addition, the pre-populated value for the honeypot web server action was for cost associated condition was a negative compared to that of no cost condition. So this the reason for this is that in the no cost condition, the adversary do not experience any negative feedback, making the instances of gains more active compared to that of losses. And as a result, the adversaries had a positive opinion, makes the adversary a positive outlook about the honeypot web server. And however, in the cost associated condition, the adversary have some negative experience, which leads to the negative perception of the honeypot web server among the adversaries. So in future, we would like to investigate the effect of different deception technologies against different effectiveness of our deception technology against various kind of cyber attacks like SQL DDoS attack and SQL injection and DDoS attack. And furthermore, we also would like to investigate the presence of different cognitive biases in the adversarial decision making in the various cyber situation. Also, we would like to test with the different combination of deception and non-deception round in a deception-based environment, to in a deception game basically. So overall, and thereafter we would like to build computational cognitive models based upon this instance-based learning theory, which could be further applicable in the real world. Thank you.